Good evening, and thanks for joining tonight's TI Technology webinar hosted by Texas Instruments, where tonight we're going to take a look at pi and pi's friends, and we're going to hopefully appreciate some special numbers in mathematics. My name is Mike Houston, and I'm the moderator for this event. I teach algebra and calculus near Pittsburgh, where I use TI Technology to make tough-to-teach, tough-to-learn concepts accessible to all my students. Tonight, I'm excited to be joined by our two panelists, Karen Camp and Irina Lublinskaya. Karen was instructor of mathematics education at Yale University for 15 years and previously taught high school and middle school mathematics for 13 years. She's been a T-Cube national instructor since 1998 and has been the author of materials for summer workshops and TI instructional websites. Karen speaks often on how to use technology effectively to enhance student understanding. Karen, thanks for being with us tonight.
Really glad to be here, Mike.
And Irina is a T-Cube national instructor as well, and she has over 30 years of teaching mathematics and physics experience at the university level as well as at the high school level. Currently, she is teaching at the Teachers College at Columbia University. She is the author of 16 books about teaching mathematics and science with technology, and has been using various educational technology for over 30 years, conducting workshops for science and mathematics teachers internationally. Irina, it's great to have you with us.
Thank you for having me.
We're expecting a large crowd, so your audio is muted. Feel free to send any questions to Irina or Karen using the Q&A window on the right side of your screen. We'll also be using the chat window to send general messages. As a reminder, the session is being recorded, and we'll provide a link to the event certificate of attendance at the conclusion of the webinar. We hope you don't have any audio issues tonight, but in the event that you do, try selecting Communicate from the very top of the WebEx menu and choose Audio Broadcast. At this point, Irina is going to discuss our agenda.
We're going to start today's webinar with a quick pi activity, since pi is the host of today's special numbers. Then Karen will continue with activities devoted to zero and slow fractions. We will look and compare e to the x and x to the e to highlight a special number e, and then we will look at the golden ratio. We will continue with Pythagoras' square root of 2, moving from there to the imaginary unit I, and our last activity will be related to harmonic series and the Euler's constant gamma. At the end of the webinar, we will have a drawing for a summer workshop registration.
And thanks so much, Irina. And Karen is going to discuss our expected outcomes.
Today, we're going to find out how we might use Pi Day not just to celebrate the number pi, but to appreciate the playfulness, elegance, and diversity of mathematics. We're going to learn about special numbers in math, such as pi, 0, phi, square root of 2, e, I, and gamma. And we're going to explore activities with TI technologies from all levels, middle school through high school, that highlight properties, applications, and interdisciplinary connections of these numbers.
Karen, thanks so much. You should have control. Feel free to share your screen.
Okay. Well, before we jump right in with all of our activities about pi and these other special numbers, we wanted to take a quick look about where do all these numbers live. I had to look up some of these values, and so I'm pretty sure that all of you listening knew that pi was approximately equal to 3.14159. But let's look at them on the number line. Here's pi. E is to the left. Here's phi, the golden ratio, square root of 2, gamma, 0. And as we all know, I is the imaginary unit, so it's not going to show up on the real number line. But if we imagine or think about this as the complex plane, the y-axis is where we graph the imaginary component of a complex number. So here's I 1 unit up. The other thing I wanted to share with you is that there are a ton of books and resources about these special numbers, lots to find out on the internet. If you're looking for some particular books, here's a good group for you to go and investigate. And I also want to take this moment to remind you of the very robust online math education community. On Twitter, you can use the hashtag T3Learns to get in touch with the Teachers Teaching with Technology community. So to begin tonight, we do want to talk a little bit about Pi, but not much because we have so many other friends to get to know. And I'm going to share with you a quick Pi activity with circles. How can we find the area of a circle? And we're going to use sectors of a circle to create a parallelogram-like shape, and it helps students develop the area of a circle. I'll share that with you in just a minute. But I wanted to also comment that last year, Irina and I were presenting the Pi Day webinar, and that webinar was entirely focused on Pi with activities for all TI calculator platforms and all levels from middle school through high school. So if you're looking for specific Pi activities, go to this link, bit.ly/sliceofpi, and you'll find last year's webinar recording and materials. Okay, so let's take a look at the activity for TI Inspire called Getting Around Area. And this helps develop the area of a circle and the idea of how Pi lives in the area of a circle. In your associated documents, you'll find the entire activity, student handouts, as well as a printout from Student Math Notes, which is a related activity, and you can see where this all comes from. But this TI Inspire activity has students taking sectors of a circle, and if we pull them down, we can see that they form a parallelogram-like shape. Now this one is kind of a curvy parallelogram, but what we can do here is show our measurements. The height of the parallelogram is radius. The base of the parallelogram is half the circumference, which is pi radius. So if you take base times height, we get pi r squared. And then the activity carries on with taking your circle and breaking it up into even smaller sectors. And obviously, as we partition it into smaller pieces, it's going to become more like a parallelogram, and you can develop the idea of a limit, that the limiting value of this is going to be a parallelogram, and it's going to be the area of a circle. So that's a little bit of fun with Pi, and now we're going to jump right into Pi's friends. Let's take a look at 0. 0 originally was developed by the Babylonians in the 2nd century BC because the Babylonians had they actually had a base 60 counting system with different symbols, and they needed something to designate which column a symbol was in, because the same symbol had different meanings depending on which column it was in, and that's where 0 came from. And this is much like we now use 0 to hold our place value. The number 1, for example, if it's in the tens place and there's a 0 following it, it counts for 1/10 as opposed to 1 unit. Okay, so what I was thinking about when I was trying to think about the idea of 0 is that students often have confusion around fractions where 0 is in the numerator and there's a number in the denominator, and the situations where 0 is in the denominator and there's a number in the numerator. They may remember you can't divide by 0. The book I had on the previous screen called 0, The Biography of a Dangerous Idea, began with an anecdote that in 1997, a large Navy cruiser was off the coast of Virginia, and this USS Yorktown became dead in the water because there was a 0 left in the computer code. And yes, they divided by 0, and it brought down the entire computer code. And so the engineers and the computer programmers had to go back, take the 0 out, and it took 2 days for them to resuscitate the USS Yorktown. So anyway, students might remember that they can't divide by 0, but they may have difficulty interpreting these two fractions. And so I wanted to have some exploration with these fractions and with slope that involves 0. Because again, students, I think my experience with Algebra 1 students is they can very easily confuse horizontal lines where the slope equals 0 and vertical lines where the slope is undefined, because some books and some teachers might call it 0 slope and no slope, and that can be a confusing terminology because is 0 no slope? Maybe, maybe not. So let's take a look at how we can work with this. Let's jump to our TI-84. Most of these activities we can do on all the platforms, and in your documents you'll be able to see adaptations whether you're working with TI-84 family or the TI-Nspire family. But let's just begin and see what happens when we divide by 0. So, when we have fractions. So we could make a fraction using the divide symbol, but I really like my symbolism and my calculator notation to match my mathematical notation. So my favorite feature of the TI-84 family is the ability to have a fraction template. It's going to be found if you're on a TI-84 plus CE, the newest version of the calculator. Press alpha and the X button, and there's your fraction template. And you arrow around the template. And by the way, you'll notice up at the top here, I have my mode set to decimal so that my fraction actually converts to a decimal. If my mode is set to automatic, it will give me a fraction. But if we just wanted to look at the decimal here, we could. The other place to find your fraction template on all TI-84 models, the black and white grayscale model and the TI-84 plus CE, is alpha y equals. That gets you to a shortcut menu, and here it is, number 1, n over d. So now let's do 0 divided by 5, and we can see that equals 0. And then let's see what happens if we want to put 0 in the denominator. If I do 5 divided by 0, I get an error message. Attempted calculation contains division by 0, and the calculation fails. Okay. Maybe we can approach this value by starting with 5 over 1, but then having the numerator get smaller, 5 divided by 0.1. By the way, putting a decimal within your fraction will automatically force a fraction answer. 5 divided by 0.001. By the way, if you're getting tired of retrieving your fraction template, you can arrow up and hit enter. And we can put in one more 0, a couple more zeros. And you can see that as the denominator is getting smaller, our result is getting larger. So even though we get a cannot calculate error message when we do 5 divided by 0, we can see that this is getting larger, 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 so we can imagine that this is going to infinity. Just let's jump over to the TI-Nspire and see what that one does. The fraction template in TI-Nspire is above the divide key, control divide. And if we do 0 divided by 5, we're going to have 0. And if we do 5 divided by 0, let's see what their message is going to tell us. If it's an error at all, it just says it's undefined. So the TI-Nspire gives a slightly different result. Okay, so now let's examine this situation graphically using slope. And we have this again on both platforms. On TI-84, go into Transformation Graphing under Apps. It's called Transform. I was already in it, so it asked me if I wanted to continue. And what we're going to put into our y equals is we're going to put in the fraction a over b times x, so we can control the two components of the slope, the numerator and the denominator, separately. I have my window set to the zoom decimal window. I also have my window format above the zoom button, second format. I have a grid line set because I want students to be able to take a look at the grid, and it helps them to count the slope. Count the units of the slope, if you will. On window for transformation graphing, if you arrow up, you get settings. And so we're going to start with a equals 2, b equals 1, and a step size 1. And here's our graph. And we can take a look at what happens to our slope as we increase a, as we decrease a. And when we get to a equals 0, we get a horizontal line. And so students can take a look at what's happening visually with that 0 in the numerator. We can also do negative slopes if we want. In any case, let's also take a look at what happens if we work with our denominator, b. On TI-84 transformation graphing, we are only allowed to use A, B, C, and D as our parameters for the changing values, so that's why I didn't use numerator over denominator or other values. Anyway, we can change B, make our denominator bigger, make our denominator smaller, and when we divide by 0, the line entirely disappears. We can no longer write the equation of this line as y equals a number times x. It no longer fits the bill. It doesn't fit that format, and that's because the slope is undefined and we've got a vertical line. Let's jump over to TI Inspire and take a look at this activity. Same thing. We can do the same thing. We're pulling on the sliders, and we have on this side of the screen, we have a y equals 4x tells us the equation, and we have the slope. What I've also been able to do on TI Inspire is I've been able to draw a slope triangle. So you can really take a look at the slope and you can see the change in the x value, the change in the y value. You can see what happens when you've got a negative slope. We've got a negative numerator, so it's a negative y value, but a positive denominator. If I've got two negatives, and if I've got a negative denominator and a positive numerator. So this is a really fun little page here if you want your students to explore with slope. But now let's take a look at what happens if our denominator turns to 0. Actually, I'm sorry, let's go to our numerator turning to 0. Same as the TI-84, we get a horizontal line. And denominator turning to 0, we're going to end up with undefined. And what I did pop in here was the equation would be x equals 0. We can no longer do a y equals. Okay, so that's the 0 activity. Let's carry on with our next activity. Our next activities have to do with golden ratios and golden rectangles. And there's a whole lot of wonderful art, architecture, opportunities to look at the golden rectangle in nature. This value was known by Euclid back in the Pythagorean age. Euclid used it to construct regular pentagons, dodecahedrons, and icosahedrons. These images that you see here, it's phi. Here's the value as a rational number. By the way, the golden ratio is not a transcendental number like pi or e. It's an irrational number because it's a solution to a quadratic equation. So it is irrational like the others, but it's not transcendental because it's a solution to an equation. So the golden ratio happens when you divide a segment up into two parts, such that the ratio of the whole segment to the longer piece is the same as the ratio of the longer piece to the shorter piece. In a rectangular form, when you have a golden rectangle, the long side is to the short side, as the short side is to this extra piece when we cut off the square. And we can cycle the golden rectangles here with spirals. And here is some of the stuff that Euclid did with them. The dodecahedron, the icosahedron here contains 3 inscribed golden rectangles, which indicate the 12 vertices. And the pentagram, the Pythagoreans thought the pentagram was a mystical divine diagram. And if you see here, the pieces of the pentagram are all in the golden ratio to each other. The red to the green to the blue to the pink are in golden ratio to each other. So lots of really fun activities that we can do with the golden ratio. And let's begin one of them by thinking about the Fibonacci sequence. The Fibonacci sequence starts with 1, and then another 1, and then 2, 3, 5. You get each term by adding together the 2 previous terms. So this list 2 has the full Fibonacci sequence. Start with 1. Let me do this. Start with 1, and 1 adds up to 2. Add 2 and 1 adds up to 3. Add 2 and 3 and adds up to 5, and it carries on. And one of the fun ways to approximate the golden ratio is to divide a term of the Fibonacci sequence by the previous term. So I can do this just by doing the math here. If I divide 1 in L1 here. By the previous term, 1, I just get 1. If I divide 2 by 1, I get 2. 3 by 2, 1.5. 5 by 3, 1.6. 8, I'm sorry, 5 by 3 is not 1.6, 1.666. Repeating. 8 by 5 is 1.6. And at this point, I'm out of my ability to do this math mentally, so let's do the math in this spreadsheet in our lists. If you arrow all the way up to L3 and press enter, it lets you come down here to this entry line. I'm going to clear those values. If you hit delete, you'll delete the whole column. You'll have to do setup editor to fix that up, but just hit clear. Press enter. Now I have a clean column. And what I want to do here is I want to take L1, sorry, hit the alpha button. I meant to hit the second. L1 is second number 1, and divide it by second number 2. And let's see what these quotients work out to be. And you can see that as we move through this column, the quotients are getting closer and closer to the value of phi, the golden ratio, 1.618 with more digits after that. So that's a fun way to have students numerically finding the golden ratio. In the TI Inspire file, we have the same thing. You can, in the lists and spreadsheet, do the division. And now the TI Inspire file also has some geometry aspects of the golden ratio. It occurs when we divide a line segment so that we have the same ratio long to short versus whole to long. And so this page here has line segment AB, and we can move point P around. And at the moment, AP is the long segment. And the question is, can we find a place where the ratio of long to short is the same as the whole segment to the long? And sometimes you get variation with pixels, but I think that this one does get there. And there it is. Point P right now has divided the segment into the golden ratio. The golden ratio, as I mentioned, can give rise to golden rectangles, where the length to the width ratio is equal to the golden ratio. And I want to share with you the construction, how you can have your students construct it. Now, of course, you could do this with compass and straight edge if you were doing those constructions in your geometry class, or you can do it on the TI Inspire. And we begin with a square, and the construction's already done for you, and the arrow clickers just advance us through the construction. You start with a square, find the midpoint of one side, connect it to that opposing corner, and this is now going to be the radius of a circle. So we're going to create a circle centered at that midpoint through point C, and where the bottom of the square extends to hit the circle, that's going to be the third vertex of our golden rectangle. There's the extra piece that gets added on. And the extra piece, as I said, that gets added on, it is itself a golden rectangle. And you can take a look at the measurements and the ratios themselves. Again, it's the ratio of the whole side to the short side of the big rectangle, and then the ratio of the long side and the short side of the smaller rectangle. And these ratios will hold to the golden ratio even if we change the size of the original square. You can pull on point A, pull on point A, you can make it smaller, you can make it larger, and you can see the sizes are changing, but the ratios are remaining the same. The final thing I have here with the golden rectangle and the golden ratio is that if we begin with a square whose sides are X, and we add on piece 1, we can use this picture of a golden rectangle to develop that quadratic whose solution is phi. So in each ratio, find the ratio of in each rectangle, find the ratio of the long side to the short side and write a proportion to find phi, and it gives your students a hint. here is the set of proportions, and if they solve that, they will get the golden ratio. Okay, moving right along. Our next friend who's coming to the party is E. And E is the base of the natural logarithm, and it was discovered by Bernoulli while studying compound interest. Now, those of you who teach Algebra 2 or talk about E in Algebra 2 or pre-calculus, I'm sure you've had opportunities to talk about it with natural logarithms and compound interest, but it sometimes feels confusing to students. Where does this number come from? And so I have some ideas that we can use to help make it pop up and show that it is wondrous and beautiful and interesting, just like pi. First of all, I just will share with you that we have some quick calculus ideas for E. And if you take the graph of e to the x and graph the tangent line, you will notice something interesting about the equation of the tangent line and the coordinates of the point of tangency. So think a minute. Do you see anything about the equation of the tangent line and the coordinates of the point of tangency? And then I'm going to move this along. Do you see anything interesting now? You can ask your students, what do you notice? And hopefully they notice that the y value of the point of tangency is the same as the slope of the tangent line. And this comes from the idea that E is its own derivative. And so the slope of the tangent line is the derivative at that x value. So E to the current x value is this y value, and that's why they're the same. Just to jump to TI-84 one more time, back in transformation graphing, if we take b and raise it to the x power, and in the second part of transformation graphing, if you take the derivative, which is here in alpha window, and by the way, if you don't have a transformation graphing that shows just two play pause buttons, two entry points for transformation graphing, it means that your transformation graphing isn't most up to date with the most up-to-date operating system. And you should always update your operating system to the newest operating system because it can give you more features and keep your calculators up to date. And so there's just more math that we can do with this. I have a particular window I have saved here. And what I want to do with the settings is I want to start with B at 1.5. I want to step value 0.1. Actually, I think I'm going to start B at 2. Okay, and so what we have here is we have the graph of 2 to the x. And the red graph is the derivative of that. And as b increases, the derivative is going to increase as well. And what you're going to see here is that as the base gets closer and closer to the value of e, it's going to get closer and closer to the same graph. It takes a little while for the graph to do all of this graphing. But what's going to happen here is students can discover that the base, where the derivative lays right on top of the graph, is close to 2.7, which is close to the value of e. So another way for students to find this value. If I go past 2.7, we can see that the derivative becomes larger than the graph of e to the x. Now, of course, when you use 2.7, and you can, by the way, in transformation graphing, just type a value. If you type 2.7, it's going to go mostly on it, but E has more digits of accuracy. It is closest to 2.718. We'll call it 2.72. And you can see it's really quite on top of it. Back to TI Inspire. Let's now talk about the comparison between e to the x and x to the e. So what happens here is I got this idea from friends on the internet, math friends, who were trying to come up with a good way to make E seem very interesting to students. And so if you play a game with your students, you can have students pair off. Each person selects a number. Person A takes their number A and raises it to the B power, and person B takes their number B and raises it to the A power, and we can see which one will be bigger. So if one of the values is 2, let's say, we can investigate the situation. So let's say A picks the value 2, and B picks the value 5. What happens when we do 2 to the 5th? And then what happens if we do 5 squared? In this case, A would win. The smaller value turned out to have the higher result when the exponential equation happened. And you could do this with several other values. You could have students eliminate. So there's one winner from each pair, and then they can find another winner and try again until you're down to just one person in the class who's winning. And you can ask students if they want to use decimals besides just integers. And you can get to one kid who's won so far and eliminated everyone else. And you can see when you graph 2 to the x and x squared that it's not that you always should pick the smaller value. You can pick here 2 to the x is bigger when it's smaller x values. Then 2 to the x will lose in these x values in between, and then 2 to the x will win over here. But what's so special about E? Well, if you get your whole class to eliminate each other, one winner, and they can go up against you, the teacher, for the final round, you as the teacher should pick the value E, and E always wins. How do I know? Let's compare the graphs of E to the x and x to the E. You will notice that E to the x is always bigger than x to the E, with the exception of the point where they intersect. And we can analyze the graph, the intersection point, and the intersection point is E squared. We can also take a quick look at this numerically in the list and spreadsheet. If you have the x value, if you have E to the x value and x to the E value, you can scroll through here and see that E to the x is always bigger until around E, where those values get very close. And then as the x value gets bigger, E to the x continues to get bigger, be bigger than x to the E. So it's a really fun way to get another cool math number into your classroom if you want to try it that way. Thank you so much for listening to those values. The party continues with Irina, and she's going to carry on with square root of 2.
Hello, everyone. Let me share my screen, and we will continue. Sharing work. Great. So we are continuing with Pythagoras' square root of 2. So a little bit of history. You already heard that Babylonians made a lot of contributions to the mathematics and to special numbers, and that also relates to square root of 2. As in about 2,000 years ago, more than 2,000 years ago, 4,000 years ago, they gave the first approximation of square root of 2 to about 6 decimal digits. And we're going to look at the activity related to the approximation. Another early approximation of the square root of 2 was given by Indian mathematicians, which was only slightly less accurate than the Babylonian approximation. Well, Pythagoreans treated the square root of 2 as the official secret and a discovery, and that's why sometimes we call it Pythagoras number, square root of 2. Moreover, one of their members, legendary, was murdered for the fact that he revealed the secret. So, square root of 2. Let's take a look at the activities here. So the first activity, we're going to explore the Babylonian method of calculation. So what exactly did they do? They came up with the recursive relationship to approximate a square root of 2 through a series of iterations. And in front of you, you see that relationship. So you take any number, you add 2 over that number, and then divide the sum by 2. You will get the next iterations, and you continue going. So we could explore with the TI-84 family, and same way you could explore with TI-Inspire as well, this particular method of calculation. So let's take a look how we can do it with the TI-84. Now, in this particular exploration, we would like to know how many times does it take to get a particular precision of the square root of 2. So let's first take a look at the square root of 2 itself. So this is the value that we would get. So let's take a look how long it's going to take and where do we need to start to get as close to this value as possible. So on the TI-84, we can track both number of iterations as well as the iterated value. So in order to do that, we're going to use braces, which is right here above the parentheses. And what we're going to do, we're going to start with the first number, so the initial value of, let's say, 2. And press enter. So our result is 0. It's a number of iterations. So we're going to do our first iteration. And then this is our initial value, which will be used using Babylonian method. So in this case, we're going to again use braces. And we're going to recall the first value, which is number of iterations. We can recall it as the first value of the answer and add 1 to it. And then we're going to recall the actual initial value of the square root of 2. And as we said, using the recurrent formula offered by Babylonians, we are going to divide it by 2 and then add a reciprocal of it. So close braces. And so if we press enter, we will get next approximation. So the first approximation when we started at 2 is 1.5. All we need to do now is press enter again to get the next approximation. So now it's the second one. And notice we already have tenths and hundredths the same as in the root 2. If we click more, then already on the first approximation, we got first 5 places after the decimal point exactly the same. So this is a very quickly converging recursive relationship. And of course, with your students, you can ask them to start at different places, like ask questions, what happens if we start at 1? What happens if we start, how fast we're going to get to the square root of 2? Now, another really nice activity is available to you on the TI website under middle school materials on the Math Inspired, and it's called Where is Root 2? So in this case, students actually use rational numbers to approximate the value of an irrational number. So let's take a look at this activity. So in this activity, first the students explore where is the root of 2 comes in geometry, and as we know, it is a hypotenuse of the right isosceles triangle with the side of 1. So they can drop that on the x-axis to realize that root 2 is between number 1 and number 2. And then in this activity, they have an opportunity to like zoom in using the scale closer and closer to this value to explore the location of square root of 2 on the number line. The activity then continues with other square roots, and it's a great way for students to explore irrational numbers. What is very interesting that the square root of 2 had to be a very interesting application in real life, for so-called A-series paper. So we can do A-series paper exploration. First, what is A-series paper? If you take a sheet of paper that has the property that when you fold it in half and align with its shorter side, it will produce another sheet of paper with exactly the same proportions as original. So the question for student explorations could be, what is the ratio of the length of the sheet of paper? This is a very simple construction that students can do. I already did this construction over here. You can use a rectangle of variable size, so it's like rectangle. And then folding paper by half means finding the midpoints on the longer side. And we are comparing ratio of sides AB and AD for original rectangle with ratio of sides EF and AE for the new rectangle, which is half of the previous one. So students can vary the sides, trying to figure out where exactly those ratios are the same, and discover that those ratios are always the same when it is equal to square root of 2. They can easily change the sizes or moving different points and then discover that. And that brings a very interesting real-life story. So that particular property of the paper was discovered by a German physicist, Lichtenberg, back in the 18th century. He discovered that when you fold a particular sheet of paper so that it's exactly half of the other one and the ratio stay the same, then the long edge should be exactly square root of 2 times the shorter edge. And this discovery was used by the country's paper industry when they standardized their paper sizes in the 20th century. And they used that ratio to create so-called A series of paper sizes. The papers in the A series, all of them, have aspect ratio of square root of 2. And you can see here on a photo of these different types of A paper, A0, A1, A2, A3, A4, and so on. The most useful or the most commonly used is size A4, which is a little bit narrower and a little bit longer than our 8 by 11 standard paper. This standard is used everywhere except North America and parts of Latin America. So if any of your students or their parents travel into Europe, Asia, they can bring that kind of paper, and you can have also real paper for them to compare the exploration. Square root of 2 closely related to other special numbers. As you see, the Yates formula here relates square root of 2 with pi, and square root of 2 can also be expressed in terms of the imaginary unit I, which is our next guess. So imaginary I, actually, it's not that recent discovery. It was first, we can find reference to the imaginary numbers in the 1st century AD, where Greeks were referring to the negative numbers and taking square roots of those numbers. In 16th century, the complex numbers were introduced in order to solve cubic equations. And then in 17th century, René Descartes called it imaginary, and the name stick. And then in 18th century, the complex numbers were used to simplify calculations of trig functions. So let's take a look at the I here. So as we know, the I appears from the solution of the equation x squared plus 1 equals 0. And since we cannot have a real number, which is square root of negative 1, we introduce an imaginary number I such that I squared equals negative 1. In this case, I is defined as square root of negative 1. Then the I may be thought visually as a vector. So let's take a look at that. The number 1 could be thought of as negative 1 to the power of 0. And the number 1 located on the positive side of the x-axis, horizontal axis, which is a real number. So we can think of this as a vector directed from the origin to number 1. Then if we take negative 1 to the first power, we'll get negative 1. So this is the number on the opposite side of the origin. So we can think of it as a vector directed from 0 to negative 1. Well, the I is defined as square root of negative 1, and square root is the same as the power of 1/2. So if we think about it between 0 and 1, 1/2 is exactly in between. So we can think of the I then to be a vector directed from the origin up along the y-axis, which is now imaginary axis, to the same length. And then, respectively, negative, the vector directed downwards along the imaginary axis is negative I. So using this idea of vectors and I, we can really think of operations with complex numbers as geometric transformations on complex planes. Now, think about it. You introduce complex numbers in Algebra 2. Students just came from geometry. This is a great way to make connections to their knowledge of geometry while introducing a new number for them. So let's take a look here. What do we mean? Let's assume that we take a complex number z and add complex number w to it. Z then can be represented as a plus bi. So a is the x component, x coordinate, and b is y coordinate along the imaginary axis, and that's our vector. Then if we add w, which we can represent as p plus qi, also having real value and imaginary part, and add them as vectors, we get a new vector whose coordinates will be a plus p for real part and b plus q for imaginary part. So very visual representation of addition. Now, what happens if we multiply, and we can think of this as a translation because it directly relates to translation as we do it in geometry. Now, what happens if we multiply a complex number by a constant which is real? Then both imaginary and real part will multiply by this number, and we got a vector in the same direction which is longer by this constant, so it's a scaling or dilation in geometry. Now, the interesting things happen when we multiply complex number by I. So if we multiply I and find IZ and multiply it through, we will get IA plus BI squared, and I squared is -1. So we get minus B plus AI. So let's take a look. If I graph this vector, minus B is right here, real part, and A is right here, my imaginary part. So this is my vector, and we can see from, again, similarity, congruence of two right isosceles triangles, that this is exactly 90 degrees rotation counterclockwise. So operations with complex numbers could be thought of transformations on complex planes. And that brings us to a very interesting activity or exploration that your students can do in your classes. And this activity was developed by Ron Armantrout, and I adopted from him. So we're going to use these complex numbers as geometric transformations to create a fractal. Imagine we have a segment from 0 to 1, and then on that segment, you created a little hat. So you broke this into 3 equal parts, and you've created a hat where each segment here is equal the same length. Then we can think about point 0, 0 is transformed through 1, 2, 3, 4, 5 different functions to get to 1, 0. And now we're going to write these functions in terms of transformations with complex numbers. So when we do that, we can create those 5 functions, and you will have a handout provided to you the materials that actually help students to build those functions. And based on those functions, we can create a program. So the activity itself, and that's the handout that you will get, provides you the opportunity to have students explore vector ideas and then explore what happens when they add a complex number, when they multiply by a factor, when they multiply by I. So the students come up with their own generalizations that we just discussed, and then the students can use this to build those functions in order to create a program. And so the program could be created where we start with a seed, a random point, and then notice there is 5 loops here. Each loop represents one of those functions, so that it's going to start and randomly pick a point and then go randomly to one of those loops to create a fractal. This program is also available to you with all the other materials. So this is that program, so I'm going to run it, and let's see what happens. So here we have 3,000 iterations, and you may notice that we started randomly in the square 1 by 1, and starting from those points, it creates a fractal, and it can start at any point and always will create the same kind of fractal. So I'm not going to run it again, so let's, due to time, but let's continue with our exploration. So when we're looking at the imaginary unit, it's a complex number, a really new, difficult topic for your students, making connections to prior knowledge like geometry and transformations, and making fun activity like creating a fractal on PI84 calculators by programming means a lot of objectives, including one of the objectives we'll focusing as well on coding. Now let's talk about our last most mysterious number, which is Euler-Mascheroni constant, sometimes just called Euler constant. It's denoted by letter gamma. So what is it? If we look at it from geometrical point of view, then it comes out from the properties of natural log and harmonic series, which is a topic in BC calculus. So on this graph, we have a function which is natural log x, and then we have those bars which represent numbers in the harmonic series, 1, 1/2, 1/3, 1/4. So if we now look at the areas of all the bars above natural log, and that's what it says here, right? Then we will get, as we're limiting number of those bars to infinity, we will get value of gamma. Okay, so that's what it represents. Now, there is some history related to this particular constant. It first appeared in 1734 in the works of Leonard Euler, and that's why it's called Euler constant, when he studied harmonics or harmonic series, exactly what we are studying in BC calculus of our students. So he used different notation for this constant. Then a little bit later, but independently, Italian mathematician Lorenzo Mascheroni used different notation for the constant, but also explored it. So we have two names in the name of this number. The notation gamma was introduced later because it was studied along with gamma function in much more advanced mathematics than our students learning in high school. But what's interesting about this number that as of today, we don't know what kind of number it is. We haven't proved it that it is algebraic or transcendental or irrational. So mathematicians today are working on trying to prove the type of the number gamma is, and it still remains to be a major open question in mathematics. Why am I talking about this? Because this is a very unique and very rare situation where our students can do something in class that makes a connection to real world, the real mathematics, the real problems that mathematicians are working with. So how they can do it? This is a great activity, a hands-on activity that could be done in class to learn about harmonic series and to introduce gamma constant. So as you see here, we're using equal tiles, same kind of tiles, same size, same structure, and the students can balance those tiles on top of each other in the following way. We balance the first tile on the edge of the table. It should balance about halfway. Then we put another tile underneath so that it's etched exactly where the first one balanced. Then we balance those two together, find a place where it balances, and put another tile underneath, and we keep going. The students can easily, if given particular background, they can easily use the formula for the center of mass to figure out how far each set of tiles is going to be from the edge of the table. So if we're using, let's say d is a half of the tile. If we're using one tile, it's just a distance d. When we use two tiles and use the formula for center of mass, we'll get that it is d times 1 plus 1/2, and so on. We can see that n tiles create a truncated or partial sum of harmonic series, and that is the distance of this very far edge from the table. But we already saw that the truncated harmonic series has a relationship to gamma. So this is the formula for gamma, which involves truncated harmonic series, natural log of n, and number of tiles used. So in a simple physical experiment with meter sticks or tiles or textbooks, whatever you have of the same size, students can actually measure the distance from the edge of the table to the very far end of this tower that they built, substitute, and calculate experimentally the value of gamma. In my classes, in my BC classes, students were doing that, and amazingly, they were able to calculate gamma to less than 3% difference with the one found by mathematicians. So what happens here then? If you think about it, then we just created this whole tower, and we're looking at the distance from the edge to the end of the tower. And the question is, let me go back then how far can it go? Can it go at any distance? So you give students exploration with the TI-Inspire or TI-84. I'm going to show it right here so that they can just build the sequence as a harmonic series. As you see right here, it's built as just 1 over A1, and then you can fill down to build as far as you want to build. And then they can find a truncated sum or partial sum of harmonic series. So here are we adding previous two numbers. Here we are adding to the sum next number, and so on and so on. And the students looking at this relationship, and you can ask them questions. So does this number ever going to converge to, or is there a limit? Is there an upper boundary to this number? The students may look at the graph and build that sequence. And for majority of the students, they would make a prediction that, yes, of course, there is an asymptote here, it converges. But it's a prediction, it's based on experiment, but is it really true? So what's really interesting here, that as we know, harmonic series diverge, but it's very counterintuitive. So while students think intuitively that it is converging, this is a perfect example where we can justify why we need to learn proofs in mathematics, because in real life, in our intuition, we only deal with finite objects, and here we're asking questions about infinity, which is very abstract, and we cannot really be sure unless we prove it mathematically. And of course, in calculus classes, students are expected then to learn how to prove those kind of situations like convergence and divergence of series, and they will prove that harmonic series diverges. And this becomes even more beautiful experiment, because it's very hard to believe that the end of that particular tower that we just showed you, like this one or like this one, could go as far as we want, and it can always exceed any next number if you pass more meter sticks, if you can build bigger towers. And with that, I would like to congratulate all of you with coming up Pi Day, and pass the ball back to Mike.
Thanks so much, Irina and Karen. As we begin to wrap things up tonight, if you have any last-minute questions for Irina and Karen, please try to get those asked. I know they'll do their best to get those questions answered. We're excited that the TCube Summer Workshops are coming. It's a great way to keep your skills really sharp over the summer. You can learn more about technology, pedagogy, content. Please visit our website to learn a little more about the upcoming summer workshops that are coming to an area near you. We also said that we're going to be giving away to one lucky winner tonight a TCube Summer Workshop registration. And tonight's lucky winner is John Sullivan. So, John, congratulations. We'll be in touch over email in the next couple of days to give you some more information, but we hope to see John as well as everyone else at a TCube Summer Workshop. To receive a certificate of attendance, go ahead and copy that link into your favorite browser. Thanks so much, Irina and Karen, for everything you shared tonight. That's getting me ready for Pi Day. I really appreciate everything you shared.
Mike, it was my pleasure. Thanks for having me.
Thank you very much, and happy Pi Day.
And thanks, everyone, for joining us. We hope to see you back online real soon. Have a great night.